Okay, question 5. In a diagram, angle AOC is a right angle and VOC is marked theta. A particle is, at O is in equilibrium under the action of three coplanar forces. So this particle just here is stationary or in equilibrium balanced forces. The three forces have magnitude 8, 12 and x acting along OA, OB and OC respectively. Calculate the value to 1 dp of angle theta. Right. What I'm going to do for this question here is, where's me highlighted? There it is. Okay, is simply look at the orthogonal axes looking like that. Okay, and you can either have this as the marked angle, as in that would be 180 minus theta, or that one there is theta minus 90. I don't mind which one. Let's call this one here theta minus 90. Okay, right. So what does that give us? Well, I've got to componentalize this force here. So here we go. We've got to separate that force to a bit going up like that and a bit going across like that. So the bit going up, well, the force is 12 newtons, so it'll be 12 and it'll be cos theta minus 90 degrees, and this one here will be 12 sin theta minus 90 degrees. Okay, so the first things first, we can resolve vertically to find theta first of all, because that won't involve x. So that's what I'll do. So part A is I'm going to resolve vertically is positive, and I'm going to be using net forces equals 0 because we're in equilibrium. So I end up with the only positive force upwards is 12 cos, and it is theta minus 90, and the only opposing force is my 8 newtons. So take away 8 newtons is equal to 0. Now all I've got to do is undo this, so I end up with cos of theta minus 90, and that is equal to 8 divided by 12. Cancel this down obviously. 2 4s and 3 is 2 and 4s and 3 is 3, so it is theta minus 90 is equal to and I've got cos to minus 1 of 2/3. Now when we're looking at this answer, we know theta, the answer for theta is an obtuse angle. So on my calculator and you cast a diagram, you know that theta can be positive here or here. Okay, so let's look at this. All I've got to do is work this out here on a calculator in degree mode. So open the calculator up. I've got shift cos of 2/3, so that's 2 divided by 3, and that gives me an angle of 48.2 degrees. So 48.2 degrees, and that is 48.2 degrees just there as well. So theta minus 90, and obviously we're just going to look at this one. It's the only one that we're worried about. Is simply going to be 48.2, because that could be read as minus 48.2, or it could be read as 311.8 if you come all the way around here. So either way, it's not this one that's needed, it's the acute angle just here. And to finish off this, you've got to add 90 to both sides. Theta equals 90 plus that is 138.2 degrees. So that's the angle we get for theta. Then we're on to part B. Okay, so part B, we end up with resolving horizontally, and I don't know, let's say to the right is positive, and we're going to use net forces is equal to 0. So I end up with the positive force is x, take away the the opposing force is 12 sin theta minus 90, and that equals 0 because we're in equilibrium. So x is simply the answer to 12 sin theta. Well, that's our unrounded answer, minus 90, and then we're away. So we're going to use this unrounded answer that I've got stored already. So x is equal to, press that, and I've got to add 90 to that. So add 90 equals, there it is. So I've got to do 12 times sin, and open brackets, it is our previous answer, take away 90. So I needn't have done that really, I should have just written 48.2. Anyway, too late. I end up with that, and it is 2 decimal places, 8.94 newtons. Okay, so that was to 2 dp, and that one was to 1 dp. Okay, I hope that helps. The answers in the book says it's it's 4 here, the second dp. It says it's 5. It's not. We've used the 100% accurate figure of this in the calculation and then rounded up. What they've done is made a mistake, and they've used the rounded up answer into here, and it's made this 8.95, whereas in fact it should be 4. I better check that before I say it. You can see 4 just there. Okay,